Hi folks, so we're going to talk about passwords and we're going a little bit deeper than the introductory, you should use a good password from a user perspective, but talk about a little bit about the theory of what makes a good password, how we store them, how passwords end up getting cracked, what that involves. We're going to talk about hashes and solved and password shadowing on Unix systems and those kinds of details, and one-way hash function algorithms. So I guess the starting point is to realize what a password is for. So it's so that we can authenticate a user. And so when we want someone to prove they are who they say they are, we can authenticate them by saying, well, do you know the password? And so many people hate passwords. It's, and the fact that everyone hates them and yet they're still around kind of demonstrates the fact that they're easy to implement. They are they work well when they work, but they have a number of faults, including the fact that people usually choose really bad passwords. So, but it can be effective, and it's like a fairly low effort form of what can be effective authentication. So, originally passwords were stored in the clear. So you would just put your password into a file on the computer system, or that's what would happen in the background. And for example, on Multics, there was a bug once at MIT where basically the password file got copied into the message of the day file, which meant that every time anyone logged into the system, they saw everyone else's passwords. So the solution to those kinds of problems is just never store the password. We can design solutions that don't require us to store the password in plain text at all. So the answer is using a one-way hash function, and you've probably run across these before. Basically, it allows you it generates a hash. So you've got some input, there you feed into it, and it generates a hash. A cryptographic one-way hash function will be deterministic, which means it will always give you the same output if you put the same password in, or the same input into the hash. And you can input an arbitrary length of stuff, and it comes up with a fixed length output. It should be almost impossible to find another input that generates the same hash, or any two inputs that generate the same hash. If you can, then that's known as a collision. If you can find two hashes that so it's two different inputs that produce the same hash, that's a collision, which is bad in terms of cryptographic one-way hash functions. And it should also be impossible to get the original input out, algorithmically. You can't have the output hash and then transform that back into the original input. The only way to get to the output is to go through the function and actually basically encode some new input and see whether you get the same output is the way that you try and find matches. So if you do use a one-way hash function, there's no need to store the original password at all. It's not technically encryption, it's hashing, because you can't actually reverse the transformation. But it is part of cryptography, which is where encryption comes from, obviously. So there's a method that most of the hashes that we use are constructed using what's known as the Merkle-Damgard construction method. And it works like this. This diagram's quite good at explaining it. Basically, we have our input, for example, our password, and we break that down into some specific size blocks. And we feed that through this function that's doing the actual encoding. There's a constant initialization vector which goes into as part of the algorithm to the first time to the function, as well as the first part of the password or whatever we're trying to hash, and then we feed the output from that into the function again, along with the next block, and so on, until we finalize it or pad it out to the length that each input needs to be, and then that gives us our hash. So common hash functions include MD5, which is cryptographically broken. It was originally done by Ronald Rivest. It was great at the time. 128-bit hash value. But since then, it's just been broken in lots of different ways. You shouldn't use it for anything that's security sensitive. It's still used quite a lot, and it's safe to use it for things like checksums to check whether your download was corrupted. But it shouldn't be used for anything security sensitive anymore because there are ways of finding collisions. SHA-1 is an improvement, and it was designed and published by the United States National Security Agencies, the NSA. It's got 160-bit hash value. It's no longer considered secure. So in 2005, there were partial collisions found. In 2017, Google announced the Shattered attack, which had the first public collision. And every year since then, there's basically been incremental improvements on that. But on the bright side, there is a significant processing power involved. So Google, for example, demonstrated 2 PDF documents that have the same hash value, which is scary. But the amount of processing power it still requires to do that is an expensive operation. So it's not likely to currently be used against like everyday end users, but it shows us that over time it's going to get to the point where those sorts of things become more and more practical. And if you hire out some like Amazon Web Computing time or something, or you've got access to enough powerful computers, you can attempt to do it. And most web browsers stopped accepting SSL certificates that are based on SHA-1. SHA-2 was also designed by the NSA, and there's a set of hash functions with various length outputs. So they produce different length outputs based on the different algorithms. It's currently thought of as quite strong, but there are some collision attacks that are considered to be practical. SHA-3 was published, and it was decided based on a hash function competition that NIST ran, and basically a bunch of different crypto like academics and people, basically cryptographers, competed to find the best one-way hash function, and the winners basically, that hash function is now known as SHA-3, and it's got drop-in replacements for each of the different lengths of SHA-2 that existed, plus an extendable output version where you can specify the exact length that you want as an output. It's probably not what you want, but it's just a feature of SHA-3. And here's a table that just does a bit of a comparison. There's the security against collision attacks here, you can see. So there are some that are, so MD5 and SHA-1 are obviously not considered to be secure against collision attacks anymore. And you can see here SHA-2 and SHA-3. And length extension attacks is another kind of attack where you append to the input of the function without knowing the original input and be able to produce another valid hash. And that's a specific kind of attack that obviously it's also good to be able to defend against, depending on what you're using the hash function for. If you're just processing passwords, it's probably not an issue, that specific attack. So, but obviously if we could have 2 passwords that produce the same hash, that would be a problem if you knew what the hash was, so that you could potentially log into a system with a different password would obviously be a problem. So how do the passwords get stored? So we still need to store it somewhere. On Unix and on Linux systems, the passwords used to be stored in a world-readable place, which is the password file. But now we store the passwords, the hashed passwords, in the shadow file, which only root or the super user can access. So the user account details are stored in etc password with this format: username, password, UID, GID, full name, directory, shell. And then, so originally password file would look like this, with the actual hashed password in there. After shadowing, the password file just has a placeholder X, and then in the shadow file you'll find all that information with the actual like hashed password in there. There's also a bunch of fields available to force password changes, like dates for when the password's valid until, or when it needs to change, and when you warn users, and when you lock the account out and stuff like that. There's a bunch of fields there as well, but often you'll see them blank like that, where they're not specified. So let's just have a quick look on a real system. So if we look here, this is an example of a shadow file on this system, where you can see that my user's password looks like this as it's stored on the system. So there's a prefix, which comes up in a slide in a second, that basically specifies what algorithms used, and then there's the salt, which I'll describe in a minute, and then the actual hash is here, so that's the actual hashed version of the password, along with some more fields that have been specified. Okay. So one of the weaknesses of one of the potential attacks against a system where we're using hashes is that if we are just storing a hash of a password, that's supposed to kind of protect our password a bit. But what if they're trying to guess passwords and an attacker just simply hashes all the passwords they think it might be, and then every time they want to attack a system, they would just look at the list of hashes they previously computed. So that's a pre-computed hash attack, and the defense is to use assault. And so, what we just saw a second ago on here is that there's a, where are we? This salt value is just a random salt that's been generated for this password, and that helps to protect against that, because this salt is included in this hash as well. So when we compute the hash, we include the salt that's just random for this account and the password input. So that means that we can't just simply pre-compute. We have to actually, every time we want to have a guess at the password, we have to know the hash and the password, and we use the one-way hash function. We combine those together, do the computational work to figure out the hashed value, and then that's our hashed password. And so if we want to guess at the password, we need to guess it, and actually compute the hash